that one too.
Okay, who wants to do number 9? One more. Yes. So the homework problems 4, 8, 9. 4, 8, 9 we're reviewing for bell work. Go ahead, Jacob.
If it's an E, can be proven by measuring mass before and after chemical reaction.
That's what we're going to do today. We're going to measure before and after a chemical reaction, validating the law of conservation of mass. So when you came in, I gave you a handout associated with this, Lavoisier, and you can see the balance there in the middle, how the masses are equivalent before and after the reaction. So let's get somebody to read where it says, at the same time in France, Lavoisier, on this cartoon here. Because Lavoisier is the one who came up with the law of conservation of mass. So we're just kind of reviewing this. Go ahead, Elijah. Oh, nice break. Just make sure you measure the mass that you put in there. It's close to being half. Nice break. Okay, nice job. So does anybody have a question about these? Anybody have a question about this? As far as the masses have to be equivalent on both sides. 28 minus 1 is 27. So we go to the periodic table. You see cobalt. So cobalt 6027 was the isotope we had yesterday, demonstrating the gamma. And how does the gamma particle ionize the gas inside the Geiger counter? That's the lab we're going to do today. How does the gamma ionize the radiation, or correction, the gas inside of the Geiger counter? Remember that? Similar to a solar calculator. So photons, that would be particles of light, they are capable of moving electrons. There has to be a certain frequency though. Red light will not allow your calculator, that is solar calculator, to work. So it takes a specific frequency of photons. And obviously the gamma is going to do it because the gamma is stronger than what? Visible light. And gamma is also stronger than X-rays. So you wouldn't want to go to like the doctor and get some gamma rays, obviously unless you were doing radiation treatments. That would be horrible. So on the assignment that I gave you today, we're going to continue with balancing nuclear equations tomorrow. And then we'll color this a little bit tomorrow as well. The reason why I'm giving you this correlates to the lab we're going to do today. So I need somebody to read where it says at the same time in France. All right, Hunter.
At the same time.
Make sure you have goggles on. Bobby, you have to have goggles on.
Mr. Sandra, this is going to be a stupid question, but can you just have 30 right there?
No, you're not going to want to use a beaker to measure the volume. You're going to want to use the graduated cylinder, pour it in there. You'll see this difference. It takes a steady hand. It's kind of like operation.
I keep going over.
I know, it's tough.
That's 125. We need 5 more.
Oh, I thought that was okay. It's gonna be 9. I'm gonna get 9.
Now, this is not what you're supposed to be doing. The reaction should be happening inside of the bag to do what? To catch the gas, right? That's why there's a bag right here. Yeah. So you can do it again. You're going to do it twice, but you're going to have to scratch that particular reaction. As well.
What? What do you want?
Make sure you keep goggles on, like Leighton over there. So good. Are you working by yourself, Trinity? Okay. That's good. That's good. So you'll probably need to wash this out and then just dry it, and you can reuse it again. Maze, you have any questions? Okay. Make sure you have your goggles on there, Melanie, when you're touching things, liquids. Got this, Ethan? Good. Now make sure you have goggles on over here. I see Abby's touching.
I can't find them.
Oh, there's a big box of them over there.
Thank you.
Daniel, you have to have goggles on.
My bad.
Yeah, you gotta put down what you're doing and get the goggles on. See these little goggles right here? See, goggles. You have to wear the goggles.
Oh shit. Is that bad?
Yeah, you're not listening to me. Put this down.
I'm gonna get the goggles later.
No, you have to go here. Use mine. Here, you can have mine. You need goggles though. Yes, you have to have them. I know. See, I have glasses on too, but you have to have the goggles. Yeah, I don't make the rules. I have to follow them though. Olivia, you got this? Now, if you use the bin right here, it's a little easier to.
Well, yeah, we've already measured that.
Okay, but if you put it on top, see it goes 0, and you hit this, and you hit 0, it's easier to put the bag on there. Hold on. Put the bag on there now. With the Alka-Seltzer tablet, and you can get the total mass without it moving around. Aja is correct. 88 plus 2 is 90. 230 and 4 is 234. RA, excellent. You got to go to the periodic table and find what number. 88, very good. 88 is radium, Ra. Yeah, 88, radium, right there. Now, once again, this is another example of alpha decay because you have 90, 234, thorium. You'll see that right here. 90, thorium. And when you have these larger elements, they're going to have the ability to shoot off a positively charged alpha particle. So when we look at the next set, if you don't see something big that would be larger than lead, you're not going to typically see alpha decay. All right, so over here on the board, we've got the alpha particle, the beta particle, the gamma, the positron. They're not labeled on the coloring sheet we gave you yesterday. So on this sheet, on the back of it, they introduce these particles, but they don't give you the symbols for them. So I'm just giving them to you right now. We got the neutron. Anytime you see a neutron, this is associated with fission, nuclear reactors. What do they use to control this? You might know. They use boron. Boron rods they absorb neutrons. So if you can absorb the neutrons, you slow the reaction. So the boron rods that go down into the nuclear reactions actually slow it. So if you want to decrease how much electricity you make, you put down the boron rods. If you want to make more electricity, which you're going to be boiling water, you bring the boron rods up, water gets hotter, you boil the water, you make electricity. And then fusion is typically from small to large elements, like happens in the sun, right? And then fission is typically where we take something large. What do nuclear reactors typically use to make energy? You might know. What's the fuel in a nuclear reactor? Uranium, or typically it's uranium-235. So that's a fairly large substance, right? 235 uranium. Okay, so as we progress today, these are the particles associated with the nuclear reactions. You got alpha, beta, gamma, positron, neutron, fusion, fission. They also introduce artificial transmutation. That's where you have something like helium that's being added to the reactant to produce a neutron. So if you see a neutron as a product, you're typically going to have artificial transmutation. It's not normal, it's obviously artificial. A lot of nice places and visit. Down the military pass, you can go to like Europe and stay in all the nice hotels there. You go to Hawaii, California, wait till your mom retires. You can take all the nice trips and stay on military bases.
I know, but I didn't